Hello, super team. All right, so after our meeting today, Lamps and I stayed late and we figured out where we were making a mistake. So recall the issue here is we wanted to show that if we looked at, well, let's see here, we got 3 to 4, 4 to 5, 5 to 3. So we'll identify that in this abbreviated notation as 3, 4 plus 4, 5 plus 5, 3. That every cycle, every one cycle is homologous to some multiple of little z. And the example we started on was the example where we looked at 0 to 5, 5 to 3, I can probably do a little better, 5 to 3, and then 3 to 0. So we had 0, 5 plus 5, 3 plus 3, 0. And here's the problem, and the reason why we were finding this so difficult to work out. This is the boundary of something. All right, we called this W, and we said, oh, we want to show that W minus some multiple of Z is in the boundary of P. But in fact, just let G equal 0. Right? G equals 0, that would mean W is in B1 of P. And it is. W is the boundary of, well, I've labeled all these regions. This is region A. The boundary of A is W. So it's no surprise that this worked out. Okay, so I want to do a more complicated example and show you how it's going to work out in general. So let's see, we'll get rid of that. Okay, so a more complicated one, and let's zoom in a bit so I can draw this. So 4, say, goes to 0. And then we'll say 0 is going to go to 1. And then we could have 1 goes to 5. And then maybe 5 can go over here to 4. Okay, and that makes a cycle because we started at 4 and we ended also at 4. All right, so our W now in this case is 4, 0 plus 0, 1 plus 1, 5 plus 5, 4. And we'd like to show that W minus some multiple of Z is, again, a boundary of P. And so here's the trick to figuring it out. We want to get a complete cycle that's going to include the purple and the blue, but we might need some more things. Actually, we can use, we don't have to use the blue, say, up here. Oops. We don't have to use this blue up here. We could make a blue part on the other side over here, which is actually what we'll do. So what I'm going to do is fill in all this stuff. Okay, and so what I claim is that if we consider the boundary of these regions, J and A and B and C and D, that is going to give me W minus GZ. All right, so let's give it a try. So what observations do I want here? Well, I'm gonna work this backward. I'm going to start computing some boundaries. Ultimately, like I said, I claim that I want to look at the boundary of, and I'll just write it like this, J plus A plus B plus C plus D. But let's see what happens when I start computing, say, a boundary of J. So J, which we can see up here, if we start at 0, is going to go 0 to 4 to 5. So this is the boundary of 0, 4, 5, which is equal to 0, 4 plus 4, 5 minus 0, 5. Okay, now what if we go to the next one, the boundary of A? So that's the boundary of, now A, we could go 0, 5, 3. And so this will equal 0, 5 plus 5, 3 minus 0, 3. And now note between J and A that we have a 0, 5 here and a minus 0, 5 here. Those are going to cancel. And pictorially, you can see what's happening. The 0, 5 line, that's right here. As you travel around J in this direction, or if you travel around A, right, following this line here, you go in this direction. Those cancel each other out. And so, in fact, anytime, because all these different faces are oriented in the same direction, if you have a face and another face with an edge in between, like this one, say, between A and B, you're going to traverse it once when you do A and once when you do B, and they'll go in opposite directions, and so they get canceled out. So that gets canceled out, and that gets canceled out. The only things that won't get canceled out are the things that are truly on the edges. So it's going to make it very easy to write down the boundary of all this. So with J, you end up with, we said the 0, 4 and the 4, 5, and you lose the minus 0, 5, that was the one in the middle. Okay, you go over to A, you don't get either of the edges in the middle, you just get the one on the edge, which is 5, 3. So plus 5, 3. We go to B, again we don't get the two edges here, we will get the purple edge. Now as we're going around, that's 1, 0. And we'll go to C, you don't have those X's, but you do have this edge over here, which is 3, 4. And let's see, over in D, you don't have this edge, but you do have these two. So one of them, as you're traveling around, is 4, 5. And then the other one is going backward is 5, 1. Okay, so let's see what we got. We can compare what we have with W. And you notice here we have 4, 0, and well, it almost matches 0, 4. And 0, 1, which almost matches 1, 0. 1, 5, 5, 1, 5, 4, 4, 5. You see, we're getting everything in exactly the opposite order. Okay, that's an easy fix. I'm going to go in and delete all these plus signs. Put an A back. Delete all these plus signs and put a minus. And if I put a minus, that is just going to negate everything that I have here. And so I'll end up with 4, 0, 5, 4, 3, 5, 0, 1, 4, 3, 5, 4, and 1, 5. All right, so my 4, 0, 0, 1, 1, 5, and 5, 4, those match up exactly with my W. And, well, now I wanted to get my Z into the game, and look, I have exactly the wrong order for all my Z's, right? So where was my Z? 3, 4, oops, I have 4, 3. 4, 5, I have 5, 4, and 5, 3, I have 3, 5. Okay, fine. What does that mean? It means I just need to subtract Z. That'll turn all those around. So in fact, W minus Z, right, is going to equal the boundary of negative J minus A minus B minus C minus D, which is in B1 of P. All right. Note we could have actually used the other side of this purple line up here. We could have used the H, F, I, K, and E boxes in the same way. So this is kind of how you set it up and how you can think about it. All right. I'm going to stop here. I'll make one more video where I talk about how we get the actual homology group.